Okay, yeah, hello everyone. We'll start in 1 minute. Okay, yeah, so glad to see you, and let's start our third lecture. And yeah, it will be about machine learning. So we are starting machine learning stuff. So today it will be introduction to machine learning, and we will discuss some problem statements, and first the most simple tasks. So in the last lecture we discussed NumPy arrays mostly, the creation, slices, and indexation. We talked about broadcasting and vectorization in NumPy, and we touched a little bit matrix multiplication, at least definition of matrix multiplication, and NumPy dot operation. And eventually, in the end of the lecture, we discussed pandas, so the second very popular library in Python, and based on NumPy. So today we will dive into machine learning. What is ML? What is machine learning? So nowadays, maybe one of the best way to answer this question is asking ChatGPT. I'm sure you know about this technology, AI system, AI assistant, and you see, I asked ChatGPT what is machine learning, and you see the answer is pretty good. So machine learning is a subfield of artificial intelligence that focuses on the development of algorithms and statistical models that enable computers to perform specific tasks without using explicit instructions. So we have no any explicit algorithms. Instead, the machine learning algorithms rely on patterns and inference derived from data. So this is very important part in ML board. It is data. We will work with a lot of different data sets, and of course machine learning models. So ML allows computers to learn from data and make decisions or predictions based on that data. Okay, that's true. So ML is built on the mathematical subjects, and it uses a lot of mathematical statistics, probability theory, and various other techniques but especially for working with data. So firstly, before machine learning, let me show you the this system of equations. I understand, yeah, it may be hard to understand, but I will try to explain some intuition behind these equations. So before machine learning, let me switch to the iPad with the same system of equation you see, and I think we should start with the definition of derivative. Maybe you know, maybe not, but what is the derivative of some function? Suppose we have function y depending on the argument x, yeah, and we want to calculate its derivative. So what does it mean? The first intuitive way of definition the derivative is simply the speed of changing. So how does y change depending on the speed of changing of the x variable? Okay, so this is delta y divided over delta x, or you can consider that this is something like y, so the first value minus the second value divided over the same difference of the argument. And suppose we have some plot, yeah, so some real function, I don't know, consider the x squared, yeah, x squared function. Then maybe you know that the plot of x squared is parabola, yeah. So this is x and y, and here is 0, then 1, and you see the difference between so the fraction of differences is something like, so if we have 2 points on this parabola, then this is almost the equation, so this is very close to equation of line. Let me draw it with red color. Yeah, so the line goes through these 2 points, for example, and if we think about geometric intuition behind this expression, yeah, so the fraction of differences, then we see that it is simply vertical length, yeah, so this is, for example, y1 minus this is y2, yeah, y2, and this is the length of vertical segment here, and the second, so the denominator is the length of horizontal line, yeah, so x1 minus x2, you see. So this is the fraction between 2 segments. And so the formal definition of derivative is, let me write it here, is y prime, yeah, with respect to x, or it is the same as dy by dx, and the formal definition is the limit with delta x goes to 0, y from x plus delta x minus y from x, yeah, and divided over the difference. So this is delta x, and it is going to 0. So this is the formal definition. Of course, if you don't know about limits, that is not a problem. You can think about this line, and you can think about the tangent of the angle. Yes, so the tangent of the angle is the same as fraction of differences. Yeah, and so we have actually 3 different definitions. The first one is simply fraction of differences. The second one, and it is the physical meaning of the derivative, is the speed of changing. So how does y change with x changes? And the third definition is formal and mathematical one. This is some limit of, again, limit of fraction of differences. And here you see we have 2 equations. with derivatives inside. So you see here is d rho by dt, so rho is density, t is time, and here you see again some different functions, and x 1, 2, 3, for example, in three-dimensional space, it will be our coordinates. And actually the first equation, if we look into it and if we think about the physical meaning of this equation, it tells us that if we fix some volume, I don't know, some cube in three-dimensional space, then the speed of changing the density inside this cube is the same as the speed of changing the not speed of changing, as the divergence of velocity inside this cube. And the physical meaning is, so if you want to count all the mass inside this fixed volume, then you will need to integrate this equation, but the sense is the changing of mass inside this cube. So, and you see this is the changing of mass, and this is the changing of mass inside cube according to the velocities. So imagine that you have some flow of water, for example, through this cube, and with time, on the one hand, the mass of liquid is changing because of some water go in, some water go out, and so on. And on the other hand, the density of water inside this cube is changing too. And of course, the overall changing of mass should be constant. So it means that this equation tells us that the mass will conserve. So this is the law of mass conservative law. And this is it. So the second equation is the law of momentum conservative, but this is not very important for us for now. But you see, before machine learning, we had to create really hard mathematical models with some partial derivatives inside and some other stuff. But these models will describe our nature with really good precision. So let's go back to the slides, and I will show you the result of solution of the equation for this flow. So you see here some tubes, and the points inside is like colored balls, colored points inside the water flow. And you see the motion of all the water inside, and this is result of modeling of the previous equations. So we need to solve them firstly somehow with some numerical algorithms, and then we can model reality with this equation. And that's all not about machine learning. So in ML, there is no preset model with equations. It is different approach. And what is machine learning? So there are three types of machine learning. The first one is the simplest one, and it is called supervised learning. This is the situation where you have labeled training data. So labeled means your data, your objects with answers. And the goal is to learn a general rule that maps objects to answers. So you want to predict answers for other new objects, not in trained data set, but in any data set you will be given. The next, more difficult part of machine learning is unsupervised learning. So this is almost the same, but you have no any labels, you have no answers. You have only data. For example, you have all the texts on Wikipedia and you want to train your model to understand the underlying structure in the data. Yeah. And the third situation is so-called reinforcement learning. This is the case when your model learns by interacting with an environment. It is very close to human learning. So we are trying something and we receive some feedback in different form, and for reinforcement learning usually it is the form of rewards or vice versa penalties, and your model is trying to increase the overall reward during all the process. And there is some agents inside, and there is an environment which gives you rewards or penalties. And this is three main areas of three types of machine learning. Let me also draw the tasks inside each type. So if we want to predict answers and we have objects, usually we use the definition of the notations of X, which is objects, all the objects. Y usually is your answers, and you need to predict to model function from objects to answers. And that's it. So your task is to find this function f. So in unsupervised learning, you have only objects, and your task is to consider the example from supervised learning. For example, you have some images, and you want to predict the class of this image, and this is your object X. This is image you see of a sheep, and the true label is sheep. So we have right answers, and the task is to model to have some function which will predict classes on the images. And your classes answers usually for classification problem, for image classification problem, it will have, I don't know, 10 classes or 1,000 classes, is not important, but you have of course some set of answers. And the task is to predict class for all the images. Then in unsupervised learning, on contrary, you have only objects X, so a lot of different images, and based on these images you need to solve some problem. For example, you want to separate the background from the actual image, and this is the prediction of mask. So mask based on your image, and mask will have once only there you have background and zero otherwise. This is the segmentation task for images. You have no answers maybe, or you can have answers. So you can, if you can somehow label your data, then you go from the unsupervised learning task to supervised learning task. Okay, and the third area, reinforcement learning. There you usually have only some environment. So this is your world, and you can think about some robotics task, for example. So you have environment or simulation, and this is environment, and you have agent which tries to do something, I don't know, for example, to learn walking. And your agent is trying to make some actions. So in each state, so environment has a lot of different states, S0, S1, and so on. And your agent, for example, starting from the first state S0, somehow select action A0 and gets the reward R0. Then, based on your action, you are going to the next state S1. Here again, you choose the next action A1 and you get the reward R1 and so on. So here you have some sequences of states, actions, and rewards. And based on this sequence, you need to learn something. So in robotics, you need to learn work. And in, I don't know, in playing chess, for example, you are trying to teach your agent to win everybody in chess. And again, you have, so in chess, it is really simple to understand that you have state on the board, you need to select some action and the main question about reward, but in the end of the game, you have some binary reward. So 1 for win and 0 for losing the game. Okay, so this is three types of machine learning problems. And firstly, of course, we will focus on first type, on supervised learning. So let's discuss this first area. Again, so X is always set of objects, and Y is set of answers. You want to predict to model some unknown dependence, which is usually called target function. So your model will give you an algorithm which predict answers over the entire set X, not only labeled part of the set of objects. Yeah. But training your model, to train your model, you need to have objects and answers. So true answers Y1, Y2, and so on for each object. And the task is to find this decision function. So the whole machine learning about this, how to define properly your objects, what answers Y can be, in what sense you want to approximate function Y, and so on. And usually, so the most common situation is when your objects describes by the vector of features. So this is feature vector. So F1, F2, and Fn is called feature description of the object X. For example, imagine that you have a car, and you want to describe a car with some numbers. Of course, we can use only numbers for training our models. So, for example, it is impossible to put strings in the feature description, because we cannot multiply and add strings in mathematical sense. Yeah. So the only way is to have either binary features. So that's clear. Is your car I don't know, electric or not? Yeah, so this is binary feature. Then you may have some categorical features. For example, the color of the car. So you need to encode all the colors. Let's say 256 colors. Yeah, blue, red, white, black, and so on. And you need to encode somehow, and then label the color of the car with some feature. Then you can have so-called ordered or ordinal features. It is almost the same as categorical, but you have some order inside. For example, the class of engine for your car. So it may be the first, second, third, and so on. So the class of engine is ordered feature. And of course, you can always have real or quantitative features. Maybe the most common, the most popular one. It can be price of car, the volume of engine, and so on. So we can think of a lot of different real features for describing a car object. And then you can train your machine learning model. And actually, you can even convert all features to binary ones. Because so for binary it is evident, so we already have binary feature. Then for categorical one, we can consider the binary vectors. So we can encode each categorical features. For example, if we have 10 colors, then we will encode them with so-called one-hot encoding, which correspond to binary vectors, and we will have one only on the component of the color number. Yeah, the same algorithm works for ordinal or ordered features, but we can somehow change it. And for real features, we need to firstly to separate our real line to some segments, yes, or bins. So we need to introduce borders, and then the binary feature will be the interval. If the value is greater than left border and is less than right border, yeah, and then it will be binary feature. So we will get one only in certain interval. And this is good, this is okay. So if we have only binary features, then of course we can train our model using all the computations inside computing memory. For example, inside Python language. Okay, so we can convert all features to binary, and this is very good for us with some losses of information, but actually it is inevitable. We need to use only numbers as features. And the ultimate structure of the objects is so-called object feature matrix. So you see here, the rows of this matrix is our the rows are our objects, x1, x2, and so on till the last object. And the columns of this matrix are our features. So feature 1, feature 2, and so on, feature n, again till the end. And this is the shape of the matrix. So the amount of objects times the amount of features, L times n. Okay, let's go on. Let's go on to the types of tasks in machine learning. Depending on the answer for classification task, it may be binary classification if you have only two classes, labeled -1, for example, and +1. It can be multi-class classification. So, for example, for the images, we can have a lot of classes as sheep, cat, dog, and so on, and it will be multi-class image classification. And sometimes the answers may be multi-class with overlapping classes. So if you don't want to select the unique class, your model can select several classes, and this will be your answer. So this is the image of cat and dog, for example, or sheep and sea, and so on. So for so-called regression task, the answer is always either real number, one real number, or several real numbers, m real numbers, and this is your set of answers. And there is other popular type of task in machine learning. It is ranking, and in ranking you have finite ordered set. For example, if you are if you're asking Google something, if you Google something, then you have your query, and your result is the page of all the results ordered by the importance, by the relevance for your query. And this is the example of ranking problem, ranking task. So the predictive model, so what do we want to train, is some parametric family of functions. For example, it may be linear functions, or it may be polynomial functions. It may be something like sinus and cosinus. So some family of different functions with parameters. So this is very important. We need to change the form of the function to model the underlying function f. And your model maps the object to answers depending on the parameter. Again, consider the simplest example of linear model. In linear model, you have only one vector of parameters or weights. So this is theta 1, theta 2, and so on, your real weights. And the function which maps objects to answers is simply dot product. You see here we multiply all the weights on the features of object X, and we sum up all the results. And this is your answer. So the answer of your model is some real number. And for example, for regression task, then your answer should be real number. And in ranking 2, it is enough. So this is the model. You can change, simple linear model, but it is enough to train. You can change weights and to predict the ground truth better and better and better. But for classification task, we need to transform this real number to label of class. Again, for binary classification, it is possible to consider the sign of this number. And sign is function which is 1, then the argument is positive, and -1, then it is negative. So sign of this number, and this is your model. So your function gives you the class label -1 or +1, depending on the model parameters and the features of the object X. So consider the same example, but in Python. This is the Python code. For simplicity, we will consider only only one-dimensional objects. You see here, this is amount, the number of objects, L equals 50, and X is line space from NumPy with 50 numbers from 0 to 30 each. And the answer will be some mathematical function. So here you see the answers y. For each x, it will be x plus 4 sinus of x and plus some random noise. So we add random noise to a little bit to have a little bit hard problem even for linear model. And this is NumPy random noise from normal distribution. So it's simply numbers between -3 and 3, and that's it. So some random numbers. Then we create 2 data sets. So you see, we want to calculate 3 features for each object, and the first data set has only polynomial features, so 1, x, and x squared. And the second data set has sinus feature inside and the first two the same, so 1x and sinus of x. Then, so having these features, we are trying to create two different data sets, so the x1 and x2. The first data set is, you see here, NumPy vertical stack, this stack. Let me remind that vertical stack is simply stacking three, in our case, 3 rows, one by one. So here we have ones like x row, then we have x row with 50 numbers inside, and x squared row. And we vertical stack them and transpose these metrics to get object feature representation. So we want our data set to be matrix with 50 rows as objects and 3 columns as features. That's why we need to transpose vertical stack here. And the x2 is the same, but the third feature is different. Yeah, so this is sinus of x, but then everything else is the same. And you see the shapes of data sets are the same, and then we will train linear model, one and the same linear model on these two different data sets. So let's go on. Here we plot the real function. So real means this is the exact formula. So x plus 4 sinus x. Yeah, this is our underlying dependence. And blue points here, they are train points. These are our data, our one-dimensional axis. Yeah. Then for each point we will have 3 features in dataset x1 and in the dataset x2. So based on these points, actually train points are our answers, yeah, and answers with noise, you see. And looking at these data set without underlying dependence, you see, it is really difficult to understand what is it. Yeah, maybe some line or parabola, but definitely not sinus. If we think without any machine learning model. Yeah, but let's try to train the models. So here we simply import linear model from scikit-learn package in Python, and you see this is linear regression. So linear means dot product of x and weights, and regression means that we want to predict one real number. Yeah, and here is inside sklearn we have realization implementation of this linear regression model. So the first model will be linear regression trained on first dataset x1. The second model will be the same linear regression trained on the second dataset x2. Yeah, let's do it. So yeah, models have been trained. Now let's compare the results. So yeah, before the results, we can ask ourselves, what does an intercept mean? What does intercept mean? So it's not an easy question, but of course we can always check the documentation. So here, let me Google it. So sklearn linear regression model. Yeah, and yeah. So the first link is sklearn documentation. You see fit intercept true, and we can simply find what is it intercept. Whether to calculate the intercept for this model. If set to false, no intercept will be used in calculations. Data is expected to be centered. So So yeah, it's not very easy. It's not very easy to understand. That's why let me show on the whiteboard. So here we have only. Here it is. We have only one-dimensional objects x, yeah, and we create three features: one, constant one, x, the same value as x, and for example x squared is the third feature for predicting the formula y, which is x plus 4 sinus x. So what is intercept? Previously you see the formula of linear regression, and the formula of linear regression is here. So this is it. And in this linear regression, you can either have the constant feature. So if f1 will be constant 1 or constant minus 1, then it means that you simply add constant theta 1 to overall sum. So this will be theta 1 plus sum of all the other features, which will change from 2 to m, and this is theta j fj. So actually the intercept means if we want to add this constant feature to the model. So if we, by default, sklearn linear regression will add constant feature, and you will have for n features we will have n plus 1 weights for your model. That's why we want to, here in our code, we want to have fit intercept false value, not to add this constant feature to the model, because we've already have this constant feature inside our data set. Okay, and let's look to the results. Let's look to the results of the linear regression models. So here we again create x1 x2 data set with the same features as in train, and then we draw results. There is results. Okay, let me rerun our code. So here we want to train, we want to define models, and then here we want to create data set. Then we want to look at the real function. Then we have trained models, and here we create data for plots. Create data. Very good. So results of the training, you see here, is very different. So for data set 2 with sinus inside, so this is the main feature to predict our underlying dependence. The green line is very close to red one. So the red is our ground truth. And you see the orange line is not so good because we have only polynomial features here, and of course any linear combination of powers of x will be some polynomial, and it is difficult to to approximate sinus with only polynomial features. So it is really important how you select and engineer your features for your predictions. And you see, actually, for good features, including sinus, we have actually a quite good result. So it's not so easy even for us looking at the blue points and to predict these underlying plot, yeah, of x plus 4 sinus x. That's why you need to think about data set, your feature, and of course your model. So here we use only the simplest linear model, and further we will go on and we will improve both models and feature descriptions. And this is the first simple example of machine learning task. So now let's have a break for 10 minutes and we will continue at 5 p.m. Okay, great. So let's continue. Let's continue with with the next slide. And what is going on? Yeah, so we actually have a method mu, which constructs an algorithm A for us based on the training set, and so the training set has all the answers, objects x, l, and answers y, l. And the representation of objects is object feature matrix, and the answers are separate vector, y1, y2, and so on. And our machine learning method mu gives us a model or an algorithm A, which then produces answers for any new object x prime. And this is the solution, the machine learning solution of the problem. So we are trying to approximate the natural law of the data set, inside data set, based on data. And of course, we need to somehow evaluate the quality of our model, of our algorithm. And for this, we need to introduce so-called loss function. This is the error magnitude of the algorithm. So for each object and for each algorithm A, we can calculate the predicted answer A from X, and somehow to compare this predicted answer with the ground truth answer Y. For example, for classification task, the loss function can be simply the indicator of error. So you see here, if the predicted answer is the same as ground truth, then inside brackets we will have false and the value is 0. So we don't deduct anything in loss function, because it is okay, we want to predict ground truth answers. And vice versa, if our predicted answer is not the ground truth answer, then it is true and the indicator of error will be 1. So loss function, we want to be as close to 0 as possible. Then other loss function for classification task could be cross entropy, some distance between two vectors of probabilities, and we will discuss these other loss function in next lecture. For regression, it is even simpler. So of course we can, for regression, we have real answers and we have real ground truth answers from the data set, from training. And for example, first variant is using absolute error value. The second variant, and maybe the most popular one, is quadratic error. So this is the square of difference between predicted answer and ground truth answer. And the so-called empirical risk is functional quality of the algorithm. So this is the quality over all objects. You see here is simply sum of loss functions on all the objects divided over the number of objects. So the mean loss on our data set. This is Q, or empirical risk. And of course, the smaller empirical risk, the better for us. We want to have 0 for the ideal model. It will be 0. Okay, and our machine learning task is essentially the searching of arg mean for the empirical risk. So through all different models, we want to minimize the empirical risk. And this is our mathematical statement, yeah? So the optimization task for machine learning problem. Actually, for any machine learning problem, there we have empirical risk and train data set, yeah? That's all we need. And again, for our example of some model, so the function g can be linear, or it can be some generalized other function, but still here we have predictions. So AI on prediction on the object X, and we have ground truth answer. And the optimization task is to find such parameters, such weights of a model, which will minimize the overall empirical risk. And of course, we encountered the generalization problem. So will we find the actual law of nature or not, or will we overfit? We will discuss later what does it mean. Yeah, and the next questions: if our algorithm A approximates the function on the training set, does it mean that we approximate the function over the entire X on all the objects? And of course, we can approximate our trained set with enough quality. So these are questions about inside machine learning that we need to somehow answer. So now let me show the simple example of overfitting. Suppose we have this dependency. Again, our X comes from the interval, it is a real number. Our feature description will be, you see here, n plus 1 features, which are powers of x, so 1x, x squared, and so on. And the formula for prediction is some fraction, yes, so you see here, y from x. And we want to, again, to train linear model. In this case, it is called polynomial regression model because all our features are powers of x. And again, for n plus 1 features, here we have n plus 1 weights, and this is our answer. Yeah, so again, you see the dot product, actually, the dot product of feature description and model weights. And this is some polynomial of degree n. So training the model, here in this situation we can use so-called least squares method because we want to minimize the sum of all losses, and each loss is simply square of the difference. So this is our answer, and y is our ground truth answer. Yeah, so the difference is our loss, and square, and sum of all the losses will be empirical risk. You can see here that I omit the fraction, the meaning, so 1 divided over L, and it is not very good, so better to add this mean. But for optimization problem, it's not important. So we still need to understand where minimum is, and it is not dependent on the constant. Yeah. So any constant, any monotonic function could be performed with empirical risk, and the solution will be the same. And here for training, we will use these points from -2 to 2. And for test sample, we will use the same points but shifted to 1/2. You see here, simple shifting. And that's it. So they are almost the same. but we will train on XL and we will check our results and empirical risk on XK, as usual in machine learning. So now let's switch. This is our question. So what do we want to investigate? So what happens to the average loss on train and the average loss on test, as the number of feature n increases. So again, we import NumPy, we create 50 objects from, so again, lean space from -2 to 2, uniformly distributed, and this is our answer for the vector of x's. We simply calculated all the answers, and the shape of data set and of answers coincide, are the same, and now we are ready to to look at the picture with our formula. So again, orange line is ground truth, and train points now are lying on this orange line without any noise, any random noise. So this is our task, and we want to train the same linear regression model, but let me explain here. This is the function of creating our data set. So you see, the first element of res list is vector of ones, and as x has 50 numbers, then NumPy ones like x will be 50 ones, and this is our first row. Then in the loop for I in range from 1 to n, we append powers of x to the list. So it will be the first power, then the second, and so on till the n-1 power. And in the end, so we again perform vertical stack of all the rows and transpose the result to get the object feature representation matrix. And our matrix will have 50 rows and n features, n features. Okay, so this is the function of creating data set. We use this function here, you see x for different values of n, and for the same one-dimensional xl and xk points. And here we are fitting linear regression from sklearn on the data set xl, and then we 2 times predict the results, 1 time for train xl and the second time for the test xk. So this in this parenthesis we have the mean of loss through all the objects. So this is vector, and in NumPy we have vector subtraction. Then we can square all the elements and then mean them. Okay. So the first train score is list of train scores, and test score is a list of test scores. Now we are ready to plot them. So this is, we calculate a lot of models for different n's from 2 to 40, to 30 to 39, and now we are plotting the result. So there is it. Again, sorry, let me update. Let me update. And I see I have the picture below. So this is the result of calculation, and you see here the train score is almost monotonically decreases, except this strange thing. You can think about it, why it is so. But the test score, you see, so the score is the average loss. And the test score, firstly, is decreasing. And it is very good for us. So the train score and test score are almost the same until approximately 20 features. But after this threshold, we see the test score is increasing, and it becomes much bigger than the train score. So this is a problem for us. We expect that our train score is small and the model works good, and yeah, we are confident in the result, but in reality the test score is very bad here and here and here. And this is machine learning, so we need to find the optimal number of features to predict the fraction, but not to simply approximate all the points from train data set. So you see, this is the good point for exact prediction, and that's it. So we can find the optimal number of features and then use this model as our final result. Okay, so this is the question, but now I think it is simple to answer. So how will the divergence point change depending on the size of training sample and why? So you need to think about, you need to compare the size of train L and the number of features N. And of course you can, at home, you can experiment with different values and to look at these plots and to understand better what is going on. So the overfitting is the problem of machine learning, then test score is much greater than train score. Yeah, and this is a problem we want to get rid of overfitting. So we see that, yeah, for extra degrees of freedom in the model, we spend all the degrees of freedom to simply precise exact fitting to the trained sample and not to the prediction of the underlying dependence. And yeah, so usually it means that you have a lot of features and you have smaller amount of objects, for example, or yeah, so. And how to detect overfitting? So the most robust way is to compare the train score and test score. Yeah, and actually let's discuss these three ways of computation for the so not the test score, but how to use these techniques to prevent overfitting and to measure the quality of your final model. So, and next lecture we will discuss some regularization techniques. So the empirical estimates of generalization ability. So the first classical way is called holdout, and this is the way we are doing now. So we train our model on, we fit our model on train Excel, and then we compare the error on holdout test set xk, and the result is our evaluation. So this is the final metric for prediction of our model, and we don't use test set in training process. Then, so on the other hand, there is leave one out control. There you train the model on all the data except one object. And when you are trying to predict, to measure the loss function, so the predictions of your model and the ground truth answer for this exact one object. And going through all the objects, so firstly you subtract first object and train on the other set of your model, then you subtract second element, second object, and third, and so on. So you see this is really time and compute consuming approach. And of course in practice we don't use leave one out control, but we need to know these, and we need to know two different sides of empirical risk estimation. So the most popular and the best way is using cross-validation. Because here you see we have training set with all the answers XL big. Then we divide these set on so-called faults. Let me show the picture. So the original data set XL. We divided it into groups, for example, into 5 groups here, 5 faults. And each time, so here we have 5 groups, we train our model on every group except first one, and then we measure the empirical risk on these, so first hold out test, this is it gives us the error 1. Then we go to the second fault. We train our model on all the data set except second group of objects, and again we measure the quality on the second group objects. And then we go through all the faults. So for 5 group it will be 5 training process for the model. We can say that we have 5 models, and then we simply average all 5 errors, and this is our final result. So the mean error of the model using cross-validation technique. And in this case we use all the data for train and all the answers for quality evaluation. So in practice, in general, we use either cross-validation technique for checking the quality of a model or holdout technique. It is also good enough and allows you to understand the real quality of your model. Okay, so maybe let's stop here. If you want at home, you can go through some selected significant events in machine learning and to see all the progress. So this is 2004, the first self-driving competition actually. Then some other historical events, and but this is really not very important for machine learning. But what is very important, there is our assignments. So maybe the most crucial part of all the learning is practice assignments. So I encourage you to solve the pandas, the third assignment, pandas course, to go through the pandas course, and then next week we will have some theoretical assignment about linear models and machine learning. And see you next week. So thank you for attention. If you have any questions, please ask. You can write them in the chat. Okay, great. Now let's stop here.